up in Einstein.
Okay, come up all.
I clicked non-Euclidean space technically manifold because locally.
No, there are non-Euclidean spaces that are not manifolds.
Chris, you asked us the same similar version that's complex, and the answer was no then.
No, the answer is definitely. There are plenty of interesting non-Euclidean spaces with geometric structure that are not manifolds. You'll see. I can give you some examples if you like. All right, so today we're going to talk about manifolds. And a little bit homological learning. All right, yeah, it's not good. Sorry. Okay, so manifolds, right. And part of the reason we're talking about this is because manifold learning has become quite a thing. There's a lot of research on it. It's a fairly hot topic. And the cool thing about manifold learning is that it allows you to kind of break some of the rigidity bounds of regression. So you can think of manifold learning as fancy regression, or even data-driven regression. What?
As opposed to non-data-driven
Yes,
regression?
as opposed to non-data-driven. Yeah, okay, so let me make my point. All right, now, yeah, I'm being a little facetious.
Okay.
I'm actually being a lot facetious.
Yeah.
Okay.
The non-data-driven regression.
Yeah, you know, stuff. Right, exactly. So what I mean by data-driven regression is, well, if you're doing a regression, you actually have to make some assumptions about what your model looks like. It's a polynomial, it's a linear thing, it's something that I'm going to regress onto.
Yeah.
The idea of manifold learning is, well, maybe you shouldn't do that. Maybe you should let the data tell you what kind of function you should regress onto.
So Bayesian?
Yeah,
But not
No,
Bayesian?
not Bayesian. Not
Why
Bayesian.
is it not Bayesian?
We'll see.
Okay.
Because there are no conditional probabilities involved.
Okay.
All right, so by which I mean here, I mean let the data tell you the function form you should regress onto. Or don't just say. Don't just say linear because it's easy. Because that might not be right. It might be easy, but easy and wrong is probably less helpful than hard and right. It's sort of a presumption more than anything else. But anyway, the point of manifold learning is to do this sort of thing. And so what I want to do is give you a little bit of information about what a manifold is and some aspects of how manifold learning operates, without going into a serious amount of detail about all the algorithms. See, part of the reason for the excitement recently is because there have become algorithms that are fast for doing this. I'm not so much an algorithms guy at the moment, so there you have it. Okay, so what is a manifold? Well, a manifold generalizes the notion of a surface. Surface does generalize the notion of Euclidean space. And it does so without much geometry. There's a little bit of geometry in there, but not a whole lot. You can put geometry into it, and when you do, then you get something called differential geometry. And differential geometry allows you to start studying what happens when you have some controlled topology and some geometry. So the observation here is these first two things, they constrain the topology. There's some very, very famous theorems in differential geometry that come out of this. I'm less interested in the geometry today and more interested in the topology. In particular, I'm interested in understanding the homology of a manifold and how you can deduce the homology of a manifold from data. So today's goal is how to deduce homology from data. And if you're able to deduce the homology of a manifold from data just by looking at the data, then that gives you an idea of what kind of manifold you ought to be learning from your data and ought to be doing your regression onto. So if you start out without any real preconceived notions about what kind of space you ought to regress onto, what kind of class of spaces you ought to regress onto, if you have some idea of the homology, that constrains the problem down quite a bit. And that drives manifold learning in some sense. Okay. All right. So, what is a manifold? Well, intuitively, you want it to be something like a surface. Okay? So, let me give you some examples of some things that are manifolds. First off, by some pictures, and then maybe some formulas. So, first sort of thing I want to be a manifold is smooth path. In R2 should be a manifold. A circle in R2 should be a manifold. Of course, I'm a topologist, that's a circle. What else should be a manifold? Well, plane, certainly. Torus. Plane. How about
Sphere?
oops, Z equals F of X, Y.
Yes.
Surface. Sphere. Yep. All these.
Hyperbolic
how about-
paraboloid.
Yes, absolutely. I can try to draw that.
How about functions of 3 variables?
Sure.
Wouldn't any technically continuous function be a,
Yeah.
or smooth
Yeah,
continuous function?
some fashion. Yeah, exactly. Right. So all those sort of things should be manifolds.
Well, we didn't say smooth manifold, we just
No,
said manifold.
I just said manifold. And in fact, there's, interestingly enough, there's a way to stick a little bit of geometry, but not too much, is the distinction between smooth and not.
So
we'll cover that.
Would the Weierstrass function be a manifold then technically?
It's a topological manifold, but not a smooth manifold.
Okay, alright.
All right. Absolutely. Yeah, that's a great example.
When you
Actually.
zoom in, it's always pointy.
Yeah,
It's a differentiable nowhere function.
Yes, it's a
It's
continuous.
continuous, but
differentiable
it's differential.
function.
It's like a fractal.
It's like a fractally kind of thing.
It is a fractal.
Yeah.
Yeah.
Yeah. So, yeah, that too is, but any of these sorts of things are. So now we need a definition that encompasses, sort of crystallizes the idea apparent in all of these examples, as well as things like the Weierstrass function, or a hyperbolic plane, or all sorts of other crazy things. Projective plane is another good one. Klein bottle is another good one. All of these kind of things. All of these kind of things are examples of manifolds. We want, in some sense, what you want to do when you're doing manifold learning is you want to be able to take some set of data living in some high-dimensional space and fit these various guys to your data. Okay.
Is there a rigorous definition?
Of manifold?
Yeah.
Yes, I'm going to write it down. Next path. Yeah. Yeah, so that's what we want. We want something that is rigorous and crystallizes the intuition of manifolds. Another particularly good benefit would be if it doesn't have to refer to anything else, really. At least any bigger space that contains it. See, by virtue of the fact that I'm drawing on the whiteboard, I've got pictures of all of these things in R2. It would be nice if I didn't have to say R2 in each of these cases. It'd be nice if I could just refer to them sort of intrinsically. So that's the definition of it.
Because adding like a extension space is already supposing something about the structure.
Well, so here's the thing. In some sense, it's supposing about the structure. It's okay if you can show that it doesn't matter how you've done that. It's okay if you can show that that sort of ambient space in which it lives is not important, as in you can swap it out. That's fine. But it kind of misses the point. It kind of obscures the point of self-etching. It's kind of like saying that you're interested in, when I say a circle topologically, I don't really have to say that I'm in R2 or R3 or R4 or whatever. The circle fundamentally is a one-dimensional kind of thing. And it's a one-dimensional kind of thing where I have 1 degree of freedom to move this way or this way, and it has the property that by the time I go all the way around, I get back to where it's. So I'd like my specification to be like that, rather than saying, I start out with the plane and I draw some set of points. That's what I'm after. Okay. So, fundamentally, here's what a manifold is about. A manifold is about, they're locally Euclidean. Which means manifolds have, at least locally, a notion of dimension. They look like Rn or something like that. Okay, so now what I want to do is I want to write out a specific kind of definition. Here we go. And I'm going to do it in 2 steps. The first thing I'm going to do is I'm going to define something that is useful to get your hands around the concept, and then I'm going to quantify over them and show that it doesn't matter, or indicate that it doesn't matter. Okay, so given I'm going to start with a topological space. I'm going to say a topological space M. So this is a set with a collection of open sets on it. Has an atlas. An atlas is a. Have you guys seen this before now?
No, I thought that said ass.
Oh. A-T-L-A-S. Like
the Greek guy.
Like the Greek guy holding the world, or like the book of maps that you no longer can buy.
So topological space M has an atlas if there's a giant.
There's a giant guy holding it up, yeah.
Yeah.
Right. Well, it's more like the book of maps. If
You actually can't still buy those.
as an atlas, if, and actually the atlas, I'm going to name it. I'll call it A.
I'm sure we should references this morning.
If A is a collection of pairs, takes a U, and takes a phi associated to the U, I'll just call it, yeah. Where U is an open subset of M, and phi U goes from U to Rn is a homeomorphism. I'll explain that if you haven't seen the topic before. So first condition is it looks like this. The second condition is if U phi and B psi. Actually, I'm using my notation here. I'll use my phis. PV are in my atlas, and they've got an intersection. Then I can form a nice little diagram. Of course, here's how the diagram is going to go. I'm going to have a U. I'm going to have an Rn. I'm going to have another Rn. I'm going to have a V. Both of these have maps going like this. U, and VB. And these guys overlap. And additionally, this phi, in both cases, is a homeomorphism. So that means that I can invert. Which means that there's a map like this. This is a commutative diagram. So, if these are such, we have this commutative diagram, and here's the constraint, and this map here is continuous. So, satisfy these two constraints. First, the structure. We've been saying about what the atlas looks like. It's a collection of these pairs, open set with a function, a homeomorphism. And whenever I take two of these guys and they overlap, then this is a commutative diagram I can write down. This function coming right out of this commutative diagram. So that's the case that I said that M has an atlas. Yeah.
What's the condition on the intersect rate?
It's not.
Oh. Fine. Not a
Okay.
Yeah, I was confused. I was like, how can feed
Yes.
the tuple?
Yeah. So this is more of an aside. This is automatically commutative diagram. Okay. So that's automatically a commutative diagram when I set this up. All right, so I've got a topological space that has an atlas. Now, there's some names for the different parts of the atlas. One of these guys here is called a chart. And this guy here, his function has a name, it's called a transition map. Charts and transition maps. So an atlas is a collection of charts such that the transition maps are continuous. So this definition, succinctly, slogan, an atlas is a collection of charts for which transition maps are continuous.
Why does homomorphism give us that there's an inverse?
Homeomorphism, right. So what is a homeomorphism? It is phi u is bijective, phi u is continuous, and phi u inverse, which exists since it's bijective, is also continuous.
This doesn't have to be.
It is an isomorphism on topological spaces. Okay. Now, some people will say the right thing to say instead of it's a homeomorphism, merely to assert that it is bijective and then drag all the continuity conditions out of the transition maps. That's totally fine. I'm being a lot more explicit here, just that it's no confusion. Now, let's soup this up a little bit. There's a modification of this. Topological space has a CK atlas if, same language but now down here, instead of continuous, I say has k continuous derivatives. Because notice, this is a function from Rn to Rn. That's good old Calc 3 land. You can talk about whether or not this function is differentiable, whether or not it has a whole pile of partial derivatives or not. So this says I can take up to depth k number of partial derivatives. It's k deep partial derivatives, and they're all continuous. So there's a difference between a CK manifold and just a plain, or a CK atlas and a plain old atlas. Now, if I have an atlas,
Is it plain atlas, a C0? Or sorry, is it?
yes,
Yes,
a C0 atlas, yes, just a plain old atlas is a C0 atlas. Yep. Now, if I have an atlas, I can add another chart to it potentially. If I add another chart and it doesn't mess up the atlasness of it, then that chart is compatible with the atlas. And so there is now an ordering on atlases. There are bigger and smaller atlases depending on the number of charts they have. If they've got a huge number of charts, and that's somehow more instructive. So now definition. A manifold. Answer, what is a manifold? Give me the definition. A manifold is a topological space with a maximal atlas. That'll suffice for what we need. Yeah.
When we say the function phi v
Yep.
compose phi v and phi u inverse,
Yep.
we say that's a transition map. In particular, it's a transition map between those two charts.
Yep. There's a transition map between those two charts.
Okay.
And notice the domain of this function. The domain of this function is not necessarily like everything, because I'm like going down to the intersection. Okay, so let me put a caveat here. Usually, it will add a few technical constraints. Under the words paracompact or second countable. Basically what they do is they rule out some really awful spaces and say those are not manifolds. Either I'm not adding them into my definition here because it just simply isn't going to come up in our discussion. Largely because I'm not going to bring it up. If someone brings up one of these awful spaces, well, I'm going to bring up the acronyms. But I don't suspect that anyone's going to do that in the span of the next 45 minutes.
Have you defined maximum atlas?
So in terms of maximal, I just did that verbally. What I said verbally is I said that if I have an atlas sitting there and I add another chart to it, and it's gotten bigger, and that may no longer be an atlas because some of these transition maps may fail. But if it still remains an atlas, then it's a bigger atlas. So what I'm saying is now add as many possible charts as you can.
Sort of like a, maximal ideal.
Yes, same kind of idea. In fact, there's a Zorn's lemma involved. And what these guys are doing is these guys are managing Zorn's lemma for you. They're ruling out some really awful things that Zorn's lemma might give you. So, nevertheless, as I said, they're not going to crop up in our discussion. Okay, so now how does this capture the notion of some of the things that we thought should be manifolds? Because this seems like some kind of machine. And in particular, this transition map business here, and whether or not it's CK or not. matters. So, comment, if M has a CK atlas, say M is a CK manifold. And when I say a smooth manifold, means K is equal to infinity. Is take as many derivatives as you can possibly imagine, and then take some more. And they're all still continuous. It is worth noting, most of the time when you're trying to avoid complexity, smooth manifolds and CK manifolds really don't have a lot of difference topologically. But C0 manifolds and C1 manifolds do. Right here.
Yes.
Oh, where does it come up? Okay. So, my point is, there's a world of difference between a CK manifold and a C0 manifold for K greater than 1, or greater than or equal to 1. But there's not much difference between a CK manifold and a smooth manifold, where K is, again, greater than 0. Okay, I'm just verbally putting that out there, I'm not going to prove it per se. All right, so now let me show you what a manifold looks like. Let's take a very simple one. Let's start with circle. And I'll show you how to build an atlas for the circle. And then, of course, the next reasonable thing to build an atlas for is things that people actually do build atlases for, which is the sphere. So here's the intuition. The intuition is I'm going to build here's my circle. Let's say, and let's even be really explicit about it, this is the set of x, y, and R2, such that x squared plus y squared is equal to 1. That set. I'm going to argue that this is a manifold. And the way I'm going to do it is I'm going to give you some charts on it. Now, I'm going to have lots of different possible charts. I'm going to give you 2 charts.
Do we need a topology?
I said homeomorphism. I said continuity. That's topology. But less facetiously. The topology of a manifold is a highly constrained, so a manifold is a highly constrained topological space. It starts out as a manifold, the definition that I've got there, a manifold is a topological space. So it's a set of the topology.
Yeah.
And then I'm putting additional constraints on that topology.
All right.
Okay. Now, those of you in complex analysis may have seen something like this before. So, here's what I'm going to do. I'm going to make one chart. It looks like this. Call this U1. Make another chart. Goes around this way. U2. Now,
You can borrow my colors if you want.
all right. Now, that's only specifying part of the charts because those are the sets. I also need to tell you the maps. I'll tell you how to make the maps. So what I'm going to do is, the blue set, I'm going to consider this line. This is the line, y is equal to -1. That line, y is equal to -1, observe at the set, this is homeomorphic to R1. So what I'm going to do is I'm going to form a map. I'm going to write a continuous function, homeomorphism. It's going to take one of these 2 blue sets to this line. In fact, I'm going to take U2 to that line.
showing that the line, the black line and U1 all intersect at the same point? The circle there, you have the little red circle and the
Yeah.
big red circle?
Yep.
Are they all supposed to?
Yeah, they're really, really supposed to be right on top of this, and that it's tangent to this dotted line.
Okay.
So the blue circle is really meant to say, I'm going to take all the points on the circle except the North Pole, very top.
Oh, I see.
Yes, so, all right, let me be very explicit about this. This is the set of all x and y in R2 such that x squared plus y squared plus is equal to 1, and y is less than 1, but not necessarily equal. The red set is basically the same specification. Y is greater than -1, taking it straight. Does that answer your question?
Yes, thank you.
Yep, all right. Okay, so phi U2 is going to map down onto this line in a particular fashion. The way I'm going to do that is I'm going to do something, I'm going to draw a line through this point. More colors? One more color, all right. I'm going to tell you where to send this particular point. This is a point x comma y, it's in U2. And where does it go? I'm going to draw a line through this point, that's supposed to be a line, and this is where it's going to go. This is phi U2 of x, y.
Oh,
Now, of course, I can do this for every single point in U2. The only point that I'd run into trouble with is, of course, the very top, but I've excluded it from consideration.
this is what the Riemann sphere?
Ah, yes, this is what happens when you do it with a sphere. Yeah, this is a one-dimensional example, or a stereographic projection. Yes, a stereographic projection. All right, so we could come up with a formula for this, just by doing the equations of a line like this. I don't really care to write the equation of that. Does anyone care to derive the equation for this particular formula? This is going to be telling me an x coordinate for some point, and this is going to be something comma -1.
So the idea is, you just want to show that that circle deleted point is homeomorphic to the line.
The line. And of course it is, because what I've done really is I've snipped here, removed that point, and just went stretch. And so it's the same topological space. Now, similarly, I can make a function with line y equals 1 and with U1 and map it up. So similarly, all right, two functions. Both of these are homeomorphisms. Homeomorphisms from their particular specified sets. Okay. Now what does the transition function look like? Well, it's actually kind of cute. The transition function does something like this. This diagram's getting a little complicated. Let me put it over here. So here's my circle. There's the lower line. There's the upper line. Let me take some point on the, let me show you what the U2 inverse compose phi U1 of something comma -1 looks like. Okay. So here is that point. I'll say this is X. Well, what I'm going to do is I'm going to first trace this back along this line. This guy is the inverse U2 of X. Then what I'm going to do is I'm going to do the same operation involving the other side. Now, I've been really super symmetric about this. Maybe I shouldn't have been. I'm going to try to modify your notes, but let me move this over a bit. All right, that's the map. So really the transition map has taken this point here to that point there. Of course it takes x equals 0 to x equals 0. And every point on the lower line gets mapped somewhere on the upper line. It's nice and continuous, there's no obvious problems anywhere.
Foreshadowing?
No. So, the end result of this is that this transition map is continuous. So, as a result, what we've got is we've got then an atlas consisting of two charts. There's an atlas consisting of two charts. Thus, if you imagine adding all the other charts that are compatible with these two charts, you end up with a manifold describing the circle. It's a manifold in which each of the things are homeomorphic to R1, so this is we say that this circle is a manifold of dimension 1. Now, you were absolutely right when you said you can do this with a sphere. Of course you can do this with a sphere. Then what do? You take the sphere, you lay it on the table, poke a hole in the top, trace a line from that hole down onto the plane. That gives you one chart. And we do the same thing on the other one. Again, two charts forming a manifold structure of the sphere. Of course, you can do this for an n-dimensional sphere, and it is an n-dimensional manifold as a result. Yes?
But how do you know that the atlas you've constructed is maximal?
Oh, this isn't maximal at all.
So how do you know that
Well,
this
so-
exists?
I can keep adding, all right, that's a good question. So I can keep adding charts, sure. I can throw on some other charts. The maximal atlas, yeah, there's a Zorn's lemma kind of argument here, which says that the largest such chain of this, basically I form a partial order of the atlases. I just keep throwing them in, making it bigger and bigger, such thing. And just declare that that thing is the appropriate atlas in question. So I'm not going to argue about whether or not there is. I'm not going to argue about all of the charts that you could put in here, but I can certainly tell you for any chart whether or not it's compatible with these two. So you can imagine listing all of the possible charts that you could draw as in possible open sets,
Right.
of which there's an uncountable number of them, but fine, nevertheless, you can tell whether or not I'm handing you an open set. It's got a topology. And I can make a map to Rn, R1 in this case. And you could say whether or not that map was legitimately homeomorphism. So imagine quantifying over all such things. If you quantify over all such charts, so essentially what I've said now is there exists a chart, two of them in fact, that cover this guy, an atlas with two charts for this. Now, I can also tell you whether or not another chart, or whether or not another open set with map is a chart. Yes? All right, so another open set with map is a chart. Okay. Now I can also tell you, given these two guys and now this new purported one, whether or not it's compatible. You can say yes or no. If it is, throw it in. Axiom of choice now. Axiom of choice says there ought to be a way that I could just walk over all of these guys, list all of the possible charts, and pick out the ones that are compatible with these two. If that exists, axiom of choice says it does, then it's the maximal atlas. End of story.
We've gone right to the axioms of math. for
Of
this
course.
question. That's a good question.
It is a good question, yeah.
So by construction, it exists.
By construction it exists, by axiom of choice. Yep. And axiom of choice is equivalent to Zorn's lemma, so you could have instead built it up level by level. Yep.
I like that.
Yeah. Awesomeness. It's math. Math at work.
Is there an example where you can't find a maximum? I mean, or it's inconclusive whether one exists?
No. No, by the same argument. So basically what you're arguing about is the axiom of choice.
Oh, I see, okay.
And I'm a card-carrying mathematician, therefore I'm quite happy to work with the axiom of choice most of the time. So, actually I'm an applied mathematician. Maybe that means that I can doubt the axiom of choice now and again. Keep that in the back pocket. Anyway.
So you carry both cards, just in different pockets.
Really, it goes to philosophy.
Yeah, of course, of course. At the end of the day, it goes to philosophy. Well, that's always the case. But at that point, I'm not necessarily sure that whether or not any of this exists, and I might as well just go home. But I'm not.
If home exists.
I'm pretty sure sleep exists, and I'd be happy for that. All right. Okay. So this is a one-dimensional manifold. The end conclusion is that this is a specification of a one-dimensional manifold structure for this. Now, the other observation is, if I write out this function, it's going to involve like a bunch of algebra, right? Like x's and y's and such. As will this one. As will this one. Of course, algebra is great because provided you don't divide by 0, you can take a whole pile of derivatives and not run into any trouble. So in fact, this is a C infinity atlas. It's a smooth atlas. Because I can like take derivatives of this fine transition function as much as I want. Okay. Right, and same kind of thing. What's that?
Yeah.
Yeah. Now, surprising fact, I'm not going to prove this at all because it's absolutely crazy. In dimensions 1, 2, 3, 4, and most others, but actually not 4, that this is really the only smooth atlas for a sphere. Dimension 4, there are actually other distinct, fundamentally different smooth atlases. In fact, there's an uncountable collection of them. Of other bizarre smooth structures. And in dimension 8, there's a list. In fact, this was one of the major discoveries of the top topologist John Milner. Was the discovery of things called exotic spheres, 8-dimensional spheres, as in set of points in R9, such that square them up, sum them equals to 1. That set. There are distinctly different atlases that you can put up.
It's not like in R3, that would be basically just planes.
Yeah. So I mean, this is the standard structure.
What would R4 look like in the design?
Well, it's the set of all points, x squared plus y squared plus z squared plus w squared equals 1. And what you do is you set that guy on the plane, x squared plus y squared, or x, y, z, and z are unconstrained, but w is equal to -1.
Right, but
And then draw the lines.
But there are uncountably many.
Oh yeah, but so they're very, very different. They're not built out of these two sets like I've done. They're very weird. They're very weird. And as I said, in 8 dimensions, there's this awfulness. There's exotic spheres. So very strange things can happen.
So to put your last point into words, then, so in R2, the only atlas is the atlas.
The only smooth atlas, yeah, is this thing. Well, in R2, it's the usual sphere.
Okay.
In R8, gosh, there are these other strange things. And there's a bunch of other dimensions in which exotic spheres exist.
Wait, so the only
Smooth atlas for this sphere in
For
dimension
this
one,
object.
for this
Okay.
object, is what I've done.
Okay.
As in to say, if you were to come up with what you thought was another smooth atlas, in fact, it would be compatible with these. Cool. Then you can add these and get a bigger atlas. So when I say maximal atlas, then it's really just one.
And you have a smooth atlas for like a square?
Ah, that is, of course, going to be my next example. So, all right, here we go. Picture time.
Professor, when you say maximal, do you mean there's countably many
No.
charts or bounded?
It means that if you were to add one more chart to the atlas, it would cease to be an atlas.
Precisely.
Just like.
So it's bounded.
No,
No.
not bounded.
No,
It-
axiom of choice is in play, beware.
It's just saying there exists a set, countable or uncountable,
There's
such
just a
that any superset over that
There's a way
would
to
fail
spec
to
it.
be an atlas.
There's a way to spec it. There's a way that there's a choice function. It tells me thumbs up or thumbs down. If I hand you
Yeah.
a purported chart, you can give me thumbs up or thumbs down about whether you're gonna keep it.
Yeah.
And if you keep all of the charts that ever could be that have got thumbs up, that's the maximal atlas.
Huh.
Axiom
That's
of
why you
choice.
can't buy atlases anymore. They're so big.
The clerks got lost in existential discussion, and the stores went bankrupt.
Kidding aside though, I mean, this really is the sort of thing that one does on the sphere. On the Earth, in fact. It really is. Here's the Earth. And what are the various map projections that you can use?
Mercator.
So there's Mercator, that corresponds, that's this sort of thing, that corresponds to an atlas, which you leave out the North and South Pole, get rid of them, and once you've popped those points out, there's a homeomorphism like that. That's one chart. Now, Mercator, however, is not going to do you very well if you actually want to get to the North Pole.
So everything gets distorted during the.
Well, it's not even in the map. Not even there. So you need something else. So there are other such projections.
You can get epsilon close to.
Well, there's some, yes, you can get epsilon close, but you can't actually get there. But there's a nice projection that goes from the top.
That's here.
No, in fact, it's just literally looking at the top of the world. So you get a cap like that. That's another, and then you do the same kind of thing for the bottom. These ones here are sort of looking down at the globe from the North Pole and looking down at the globe from the South Pole. So here's Antarctica, and in this one here you see, oh gosh, I'm gonna make a mess of this. There's Alaska, there's Europe, or Asia rather, and let's see here. Blah, 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 stuff. So there's Europe, Asia, North America, and then like Africa down there, North Pole. So this forms an actual atlas in the usual sense. In the mathematical sense, this is an atlas. In fact, actually, USGS puts out a big, thick book on map projections. Literally, that book is an atlas in the mathematical sense. I once had to deal with that book, to deal with GPS errors in geolocation. It was not very fun. It's just about as unfun as one can get and still be doing cool math.
Was it Apple Maps?
No, it's not Apple Maps. No, I mean, it was literally this paper book that you flip through, and there are the formulas describing the homeomorphisms in question. Although they didn't list it as such, but that's what they were doing. Craziness. Anyway. Right, okay, so the question about the square. And I gotta get to a little bit of manifold learning as well. All right. So here's the square. Well, here's the problem with the square. The problem with the square is that it has these corners. Right? And these corners are going to be places where if you just look at a single chart, you won't necessarily know that there's anything wrong going on. So in particular, let's say I look at one particular, let's zoom in on this particular open set. And let's also look at this open set here. Now, these are homeomorphisms, which means the only constraint that I've got to have on these guys is that they're continuous. There's no notion of differentiability on this set thus far. No notion of distance thus far. So let me do the following. Let me tell you these are supposed to be open sets in R1. Let me mark off some tick marks explaining where the points are. That's one of them. Nothing wrong with that, it's homeomorphism. So what that says if you move a little bit over here, it looks like you're moving very far in the coordinates, but again, it's a homeomorphism, you really can't tell. This other one here doesn't do anything unreasonable. Now if you form a transition map, however, some trouble ensues. Transition map is a function from R to R. And what ends up happening is over here in the overlap, let's just say this is 0 right here. In here in the overlap there's no real problem. But what happens right at this corner? What happens at this corner is that your nice continuous curve, it's still continuous, but the derivative is discontinuous.
Derivative of what, the square?
The derivative of the transition function. This is a graph. This is a graph of phi u2 goes to phi u1 inverse of x, y. So that function has a discontinuous derivative. So I just didn't know any better. This would not be smoothly compatible. These two charts are not smoothly compatible, but if I put them into my atlas and declare that that's an atlas, then this then gives me only a C0 atlas. So the conclusion is putting U1 phi U1 and U2 phi U2 in an atlas yields a C0, but not C1 atlas.
So it's the map of your transition function?
Now that's the map of your transition function. So it's got this discontinuous derivative, which is to say that one of them starts going way faster than the other. In particular, as I start moving along in U1 here, moving very quickly compared to U2. Very
What are the tick marks representing?
The tick marks are representing equal marks in my real line. Basically in the coordinates. You can think of the Rn, the range of each of these functions, these chart functions, as being the coordinates you're reading off on your GPS as you're wandering along in this manifold. That suddenly, as you're moving along here, you rack up a very large, the coordinates get really big over here, where over here they don't. So actually, oh, you know what, I guess I've done this backwards. This is backwards. This is U1, U2 inverse, actually. Got that backwards. Okay. Of course, if I had done it the other way around, then it would have been more like this. Nevertheless, still discontinuous. So yeah, if you have a corner in your manifold, and you want to represent that, this is the way it shows up. It's kind of subtle, honestly, because it's not like it's discontinuous. I mean, it's not like a discontinuous function. It's still a C0 atlas. And the fact that I'm showing that corner in there, or the way, because I'm putting, rather, how I put that corner in there, is by specifically declaring that these two guys are in the atlas that I'm talking about. It's a little weird, but nevertheless, that's the right way to think about it. it's very similar if you played around with parametric functions before. A function of one variable that takes a vector, say three-dimensional vector as output. It's very much like that. In fact, this is a nice generalization. Okay, so now let me fancy this up a little bit, because of course, as part of the theme of this course has been, there's always a category theory angle on things, and there hasn't been any category theory in this lecture at all. It's time for the category theory to come back. I need a category of manifolds. The objects are manifolds. The morphisms are going to be something like continuous functions between topological spaces, but they've got to play well with the atlases. And in particular,
They have to be atlas preserving?
they have to be atlas preserving, exactly. Which is to say that they're going to play the role of differentiable functions. Functions that have continuous derivatives. Okay. I think that's a good place to end on, so we'll take you into the definition of that, and then next time we'll pick up the manifold. Because really what I need in order to talk about that is something called the tubular neighborhood theorem. All right. So, okay, functions. Definition. If M with an atlas A and N with an atlas B are manifolds, and F is continuous, so I have a continuous function. That's a manifolds. Is a CK function. F, well, it's going to do something with regard to the manifold. It's got to play well with the manifolds. It's got to be manifold preserving, right? So here's my manifold M. Here's my manifold N. Let me take a chart out of here, call it U. So U is a subset of M. We take chart here, V is a subset of N. So each of these guys are charts. Here's my phi U. This is Rn. Here's my phi V, also in Rn. And I've got up here at this level, I've got F. Now we run into a little bit of a problem if I try to make F work on U. Why? Why can't I just say that F is a function taking U to B? Something a little funky about that. F is a function on M, yes, and it takes values in N.
You can't guarantee that at the end of it.
Yeah, the domain here might not mean, strictly speaking, the range of this is, gosh, in N somewhere, but not necessarily in V. So I need to put a constraint. Whenever F of U is contained in V, for a chart, U, phi U in A, and V, phi V in D. If that's the case, now I'm good to go. Now I can put my F down here. So given that constraint, I can put my F down here. Now I'm in commutative diagram land. What am I going to do? Well, I'm going to come up this way with an F, a phi U inverse, and now I'm going to compose 1, 2, 3 to define a function down here. The function down here looks like phi U inverse composed with F composed with phi V. This is kind of like a transition map, except that it's got F stuffed in there. notice this is again a function between Rn and Rn, so you can reasonably talk about calculus. Tell me that whether or not that function is differentiable or not. And if so, then this is a CK function. Now, if I have two CK functions, one after the other, go from M to N to P, well, if both of them are CK functions, then their composition is a continuous function. The identity function from M to itself, is that a CK function? Certainly continuous, certainly homeomorphous, but is it CK? I already said the answer, as it happens. So it's the identity function, the CK function. Well, what happens if I pop the identity function into this formula?
Yeah.
Nothing. Well, it'll not quite nothing. What do I get? I get what kind of function down there?
More like a function back.
And if I put in an identity function here, these two guys are not the same.
Oh, sorry.
Phi decomposed with phi.
Right, which is a transition function, which is by assumption CK.
Which you put in the identity instead of F.
Instead of F.
Oh, okay.
That's right.
All right.
So, facts. Fact number one is the identity function on a manifold is CK whenever M is CK. The second thing is I can compose. CK functions. They are functions, they're associative, and therefore, thus, there is a category, usually called man K, of CK manifolds with CK functions as morphisms.
That's a M.
M-A-N superscript K. Man for manifold.
The manually has small categories.
Manually small categories, I suppose so. I suppose that would be for C infinity, I suppose.
Yeah.
All right. So there's a category of manifolds, and that's a good place to work. Now, what's kind of neat about this, what happens if I chose different charts? Say I chose a different chart here. Let me just choose a U prime over here. And I chose over here a V prime. Well, I've got transition functions going on over here too. I've got transition functions going on over here too. This is phi U prime inverse composed with phi U. Similarly over here, this function is phi V inverse composed phi V prime. If I compose all of these guys together, you get something that looks like this. Phi V prime composed F composed phi U prime inverse. What does this mean? Well, this means this transition function business is something that really is kind of insensitive. It's really kind of an invariant. The neat thing about this is if you start writing down the partial derivatives, remember this is a function from Rn to Rn. You get a lot of partial derivatives potentially. If you just work with the first partial derivatives, you can put them in a matrix, the Jacobian matrix. This also is a Jacobian matrix. Jacobian matrix, Jacobian matrix. Different charts. That's a Jacobian matrix, that's a Jacobian matrix. This too is a Jacobian matrix, so there's a whole bunch of matrix multiplication going on. If I write this thing out, it's going to be my final point here. If I write this out, oops, did it completely backwards. B prime, B, composed with one in the front. There we go. I'm going to do it like this. This is a multiplication of three matrices, three Jacobian matrices. This is performing the coordinate transformation on the input, the coordinate transformation on the output, and this is the Jacobian matrix in the middle. This is known in linear algebra as a similarity transformation. Run across similar matrices? No? Okay, well now you have. Similar matrices basically are what happens when you do a basis change. If you take one matrix, you write a basis for it, for that linear map. And then I say, well, I don't really like that basis, I'm going to change the basis. I get a new matrix representation that is somehow the same map. It's a similarity, that's called a similarity transformation. That's what's going on here. So what this means is that the moment you have a C1 manifold, you can start doing, instead of studying manifolds by way of topology, you can start studying them by way of linear algebra. Now, that's been the theme of this whole course, which is taking a topology and turning it into linear algebra. This is taking topology and turning it into a linear algebra in a fundamentally different way. It's an entirely different way to study topology from a linear algebraic standpoint. And in fact, the neat thing about manifold learning is it puts these two ideas together. It's a great place to end. See you next week. And I will circulate around a list of times when the final presentations will be, now that I've got all the topics in hand, and we'll go from there.
I was supposed to send you an email about that.
But I did write it down, yes, okay.